Welcome to the lecture for chapter 2. And hopefully you're watching this right after you watch chapter 1. And what I want to let you know is that these lectures, especially the chapter 1 lecture, got a little bit long because I walk right through all the material. It's not the same as if we were in a classroom where I'd stop and ask you questions and get you to give feedback to me. So at any point where you don't understand something, or if I'm going a little too fast, you can stop it, pause the thing, go back. Make sure you're understanding. If you don't want to sit for more than 10 or 15 minutes, pause it. Get to a slide and pause it. Get up, go get a drink, get something to eat, whatever you want to do. It's easy enough to make my lectures shorter. I will try not to ramble on or do too much, but sometimes the chapters are kind of lengthy and the materials a little bit lengthy. And I'm trying to have one lecture per chapter. In this case, we're up to chapter 2. It's surveying mathematics, and it's not too much for me to deliver. It's pretty much math, and it's pretty much covered in the textbook. I will hit the highlights. I don't expect this one to be very long, but this is where some students have trouble in beginning to do the math. So if you have questions, like I said before, email me. If you send me an email, follow that up with a text message, either to my office phone or to my cell phone. Either one is going to work. Remind me that you're a student, that you have an issue. I've only got a few of you in the class. It'll take a moment or two to remember your names, but I'll get there. But if you have troubles now, is the time to ask me. Ask me at the beginning of everything. So I'm going to share my screen, and we're going to start with chapter 2. And we should be sharing right now. There we go. So chapter 2, surveying mathematics. As I said before, I think one of my intro videos, when I was in high school, I took calculus, and again, it's not even offered anymore. It's a shame that the math I took in high school at St. Mary's County is not offered anymore in Southern Maryland, period. It's now taught at the college level, whereas I had a very good background of calculus in high school. And back then, I wondered, what am I going to do with all this math? I mean, I was kind of good at it, but what am I going to do with it? Well, I found a job. Surveying is math oriented, and when I started, I was constantly using math and trigonometry. So these are the things that are sort of fundamental, but they're important, as the slide says. You will be converting some units. We will deal with lines and angles. Surveyors deal with polygons. Polygons are multi-sided shapes. A triangle is a three-sided polygon. A square or rectangle is a four-sided polygon. A stop sign is an eight-sided polygon, an octagon. So we use trigonometry, dealing with triangles. Surveyors do that on a daily basis. At least we used to. Now we have computers and data collectors that do it for us for the most part. But I still would do some trigonometry every now and then. We work with circles. We work with arcs. Earth is a circle. And I explained it to you before about rectangular coordinates or state plane coordinates and northings and eastings, and surveyors will certainly work with those things, those items. So that's an overview of some of the important fundamentals of math that we're going to utilize. This is for decimal conversion to feet. Surveyors measure in hundredths of a foot. We don't measure in half inches or quarter inches or even inches at all. It's much like the metric system, how things are broken down into hundredths and tenths and thousandths to make math easier. Surveyors work in decimals of a foot. Simple conversion here would be 6 inches. You know that's half a foot. 12 inches in a foot, 6 inches is a half a foot, or it's 0.50 feet. That's what surveyors measure in. You can see here that an inch is 0.083 feet, and that 3 is repeating. And therefore, surveyors get down to a hundredth of a foot, which is 0.01, or we measured approximately an eighth of an inch. If you look at a tape measure, an eighth of an inch, and you'll notice that that's the level of accuracy that surveyors generally get down to. Some equipment allows you to get down even tighter than that, smaller than that, to where you're measuring the 16th or a 32nd of an inch, or you're in the thousandths, as surveyors would refer to it, thousandths of an inch. Most of my work is going to be in the 1/8 inch or 0.01 accuracy. 0.01 feet would be where my level of accuracy is. These are rudimentary exercises to show you how to convert units. If you have trouble converting units, I have a little bit different technique that I've learned in converting my units, but it's essentially still crossing all these things out and you end up with the measurement, the unit that you want at the end. These are all examples, and you can look at the slides as well. There's examples in the book of how to do things too. Here we're looking at perimeter. It says here lines in construction drawings. Well, that's true. You're looking at a perimeter of a building. Why would anybody want a perimeter of a building that you want to measure, and how would you get to it and do it? A lot of reasons you want a perimeter. You want to know the square footage of the building, the area. Buildings, as they're so large, and the different square footage require a lot of different components, whether it's parking or stormwater or fire protection. All those types of things go into play. If you want to know the area of a building, you need to know the perimeter of the building as well. So you'll learn these things. The book is pretty clear on a lot of this basic concepts in math. Here, you can reference these. The next couple chapters these next few slides are in your book, the materials in your book. And you may want to reference them as we deal with things about perimeter or area, but these are simple formulas that will help you determine the perimeter and the area of your basic shapes. A little bit different. Here's your typical slide that this will show interior angles. We'll get to that. The book talks about it a little bit, about the importance of interior angles, and that everything has to add up to the right number of degrees. But as a construction surveyor, not surveyor, but construction manager, and dealing in the construction industry, this is something that you're not going to have to worry too much about. I'll briefly explain it. The book talks about it. It doesn't hurt you to know a little bit, but it's not something that you're going to find too applicable in your industry. This is back to your basic rules of geometry. The isosceles triangle, these two angles are equal. All three sides are equal. Equilateral triangle, all angles and sides are equal. Different types of triangle, that's your typical right triangle. This is the most common triangle that surveyors solve. When I started out 34 years ago doing this in this business, I was using right triangles and trigonometry hundreds of times a day to solve the triangles. And I do mean hundreds, sometimes 200 times in a day, I would solve a right triangle for what I was doing outside surveying on a field crew. Here's the different types of right triangles. 30, 60, 90. The isosceles again is equal. Everything's equal here. These are different types of triangles here. This is a oblique triangle, where this angle here is greater than 90 degrees, and then this is one where it is 90 degrees, a right triangle. And one of the things you can remember is they're trying to show you the 3, 4, 5. If you ever want to know something is square, you go like a board you cut, you would measure 3 feet in one direction, 4 feet in the other direction. You make a mark in each one. And then if you don't have 5 feet across, you're not square. So that 3, 4, 5 triangle is a key for a lot of construction layout. If you're checking things as a manager or as a site super or something like that, you have to remember that for practical use. Again, this is just right triangles labeling for you. Just remember when you're dealing with the text in the book, the capital letters are your angles, and the opposite lowercase letter is the distances. And this graphic clearly shows that. So here, again, we use trigonometry in surveying all the time to solve triangles. So you probably have various ways to remember sine, cosine, and tangent. I've had, my granddaughter tells me SOHCAHTOA is how she remembers it. S for sine, O for opposite, C for cosine, A for opposite, that's your SOHCA, and then TOA, tangent, is opposite over adjacent. I remembered it as sine, cosine, tangent. Oscar has a heap of apples. I would say that to myself. I'm out surveying and I needed the cosine of a triangle, or I needed the sine of a triangle. I would literally say in my head, Oscar has a heap of apples, and I would know which function I was using and how to use it and how to get the answer in my calculator. So you need something to help you remember sine, cosine, and tangent. That will help. I'm not going to go through examples like this in the slides. You can look at them. Again, if anybody has questions with math, let me know. Here you're starting to see practical application of how we would do something and why. You got this 8-lane highway. You're over here measuring, but you want to know where this point is. Maybe this is a radio tower or a satellite antenna or something like that. Well, you don't want to cross, you can't cross the highway because it's too dangerous, or maybe there's barriers, or maybe there's big fences up. But you can locate it from over here by turning angles from known points and use trigonometry to solve for this location. The book walks you through these type of things, but this is a real life application of doing something with trigonometry, and I've done it several times, locating radio towers primarily. Here's some more formulas that you'll need. You might want to hang on to these for a couple chapters, and once we get past the midterm exam, you're not going to have to worry about any more math in this class. Again, I'm not going to go through these, it's just sort of redundant. But again, this is the real life example of how you want to do something. When you have an obstacle, if I'm here and I need to get to there, how do I do it? Well, I don't know what that is. I can't see it. So I can set up over here someplace and I get this distance and this distance, turn this angle, and I can use math and trigonometry to solve for that distance, as well as these angles, and get all my positions straight by using trigonometry. So while some of this might seem to be some basic math, or some of it you might think is difficult, it is a real life application of math in the surveying world. Here, this is something that you run into. I did it frequently. I probably solved, any given day I could solve 2 or 3 dozen oblique triangles. They're a little bit harder. They'll give you a formula for it, but oblique triangles are triangles that do not have a 90-degree angle. Here is your areas of dealing with triangles. Here's an example where you have three distances. How do you get the area of it? So it walks you through these different things, and they're all good examples. It's pretty clear to follow. Back to the building situation, how to do that. Here we go. This is kind of important. I want you to understand these components of a curve and why there are curves and why surveyors need to utilize curves. So yes, we have an arc. Let's just say this is the Earth itself. We're actually measuring along the arc. That's one of the things we're doing. So when you're using satellites, receivers, and real-time kinematic surveying equipment, RTK, or real-time network solutions, RTNs, you're actually measuring on this surface, you're hitting this arc, and it's doing various things to flatten you out. But surveyors tend to use arcs for streets, right? We have to have curves in streets, and we're going to talk about this later on in the chapter. We're going to get pretty specific on how to do some of the curves and things that you would utilize the math for. But just keep in mind the parts of the curve. This is your tangent. You have two straight lines. Well, if you have every road had straight lines, you'd always have to come to a stop and make a turn. And you know that you can't do that. How long would that take you to get down 301 if every time you needed to make a bend, you couldn't make a curve, you had to come to a stop and then accelerate again and come over here. It just would be a waste of time, resources, and everything if roads didn't have curves. So you have a tangent. That's where you the straight section coming in, the straight section going out. You have a central angle or a delta. That's your Greek symbol delta, Greek letter. This is the delta. And these two lines are your radius lines, right here and right here. And the thing that you're going to want to know about is this right here is a chord. That's from the beginning of the curve to the end of the curve. And of course, that's the arc on the outside or the length of curve. Those are your components of the curve. The book's going to have you do a little bit here with math, but we're going to look at the components of a curve later. Here, we're looking at area. You have to use pi, the function that's on most of your calculators, I'm sure. Used to be a big thing, how many decimal points do we remember pi to? And the reason for that was because we didn't have buttons on the calculator. So it was like 3.141596 or something is like, you know, as far as I ever remember, but the more you could remember the number, the more accurate your answer was, because we always had to key in the constant for pi. Formulas for areas of a circle. This is your rectangular coordinate system that we talked about. And notice these marks, each mark here is 100. This would be a northing of 100 and easting of 200. You'll have to do some things with this, but surveyors utilize these coordinate systems to plot the points on the ground, or I'm sorry, take the points that they locate on the ground and plot them on a map or inside a computer. And we assign coordinate values to everything we occupy or shoot. Everything has a 2D or 3-dimensional coordinate on it. This was a formula, This was a formula that I used often, a whole lot actually, inversing coordinates to get a distance in between. We always had to know what our distances were in between things. And there was also ways to calculate the bearings in between points so that we could figure out where we were going, the direction we were in. So all these things here are important, and you'll have to do a little bit with each one of these. Here's the angle. Like I said, you're inversing these coordinates. the way this is written here, you have two pairs of coordinates, remember? This would be, say, pair 1, or pair 2, we'll say that's pair 2. This is pair 1, 0, 0, 100, and 200. If you want to figure out the distance from here to here, from pair number 1 to pair number 2, that's this slide right here. You take the easting of 2 minus easting of 1, square it, plus the northing of 2 minus the northing of 1 squared. The whole thing is, you end up taking the square root of it, and then you end up getting the distance. Here is how you get the angle between the two, like the bearing, the compass bearing between the two coordinates. Here we're going to walk you through a little bit of what I just described, and this is where you begin to get your examples of how things are going to be performed in the field. So that is the end of these slides for section 2. I'll stop sharing, and now you get my face again. So I went through that a little quickly. It's not important for me, I don't think, to go through every example or teach a math class. I want to see where you're at, and then I can help you. So this concludes lecture for chapter 2. Again, if you have any questions, please feel free to contact me. And again, next week we're off. You're off for spring break, and then we'll come back with module 2. And at the beginning of module 2 is when I'll have my office hours at 7 o'clock on Mondays, and I will communicate with you and make sure everybody understands that with the email. So I hope you have a wonderful week, and that you are able to grasp the material, and that you begin to enjoy the class. Take care.